Thanks a lot for the invitation to talk at this very interesting conference. And my topic today is, as mentioned here on the title slide, historiography of the Pythagoras theorem and the Sulbasutras. So Pythagoras theorem is in quotes because actually, as we will see, there's a lot of myth going on with this term Pythagoras theorem. I mean, there's a lot of it's very problematic, as we will see in this presentation. So, as Swati ji has mentioned, I'm the author of this book, The Imperishable Seed: How Hindu Mathematics Changed the World and Why This History Was Erased. So, in this book, I spoke about how most of the mathematics we learn in school today comes from the Hindu civilization, and also its deep connections with the Hindu philosophical and spiritual thought and knowledge systems. And also my aim was also to show why we don't know so much about it in these days, why the mainstream narrative of mathematics has literally pushed this Hindu mathematics out of the picture. So these were some of the things that I've addressed in this book. And as while researching for this book, and after I wrote the book also, I kept up with my researches in Hindu mathematics, and I came across more and more interesting information. And one which I found really very interesting was this whole historiography of the Sulbasutras and the so-called Pythagoras theorem, because here we see very clearly how histories are shaped, how narratives are shaped, and how propaganda is also created to impose a certain historical picture in the mainstream. So this, for example, I've just stated here on this slide. If you ask some people, have you heard of the Pythagoras theorem? Of course people say yes, of course I've heard of it, and they will also believe that it was discovered and proved by Pythagoras. And but if you ask the same people, have you heard of the Sulbasutras? They will be totally flabbergasted. What are you talking about? That sort of a reaction you will observe. And also I noticed this trend very much in the online portals, the online sources of information which spoke about the so-called Pythagoras theorem. They would invariably mention Babylonian sources, but Sulbasutras would be just mentioned as a footnote. And this made me very much interested in investigating this further, why it is like this. So in fact, the Sulbasutras, they are one of the oldest mathematical documents in the world, and they contain the first ever general statement of the so-called Pythagoras theorem. So in fact, one would imagine that the Sulbasutras would have received much more importance in the history of mathematics. So but it is unfortunately not the case, and this is what will be addressed in this talk. So I have written 3 articles on my blog, and I will be in this talk. I will be presenting a part of the information given in those articles. So I'll be discussing basically these articles from my blog, Substack blog, Sulbasutras and the Pythagoras theorem, and square root of 2 in Babylonian mathematics and the Sulbasutras. There's also a third article, the big square with the missing corner, I've titled it. So this deals with one of the techniques used in the Sulbasutras to find an approximation for the square root of 2, and how this can be extended further to get an infinite series for the square root of 2. But I will not be addressing that in this talk. So what are the Sulbasutras? I think many of you would be aware of that, but a very quick recapitulation. Basically, the Sulbasutras are you can consider them as appendixes to the Vedas, and they deal with rules, geometric rules for the constructions of Vedic altars. And these constructions were carried out, measured. These measurements were made with the help of the rope. And Sulba means rope, so that means basically that the sutras for the rope. This is what the Sulbasutras literally mean. They used to, and yeah, there are also astronomical information. So for example, how to find out the directions, east, west, north, south, so-called circle method in the Katyayana Sulba Sutra. And as far as the mathematical and geometric rules are concerned, they deal with creating altars with a given area, or the area which consists of the sum of the areas of 2 other altars, or you kind of you want to make a new altar with the same area as an earlier one but a different shape. So those kind of geometric rules they abound with such kind of geometric rules, and in these rules there is a lot of mathematical information hidden. And this is also a topic of research even for today, because the question arises how these rules were formulated, what was the background behind these rules, because these rules are given just without any mathematical justification, because the Sulbasutras are not mathematics texts, they are texts for making Vedic altars, right? This has spurred on a lot of research in the history of the Sulbasutras. So, I mean, in spite of that, of course, the fact remains that they are not well known in the narrative, mainstream mathematical narrative. So, and there are different Sulbasutras penned by different, formulated by different people. So the Baudhayana and the Apastamba and the Katyayana Sulbasutras, and they belong to the Vedic time, and they are like part of the Vedas. They can be called as Vedic mathematics in the true sense of the term, because they arise from, they are from that time. Okay, so right. Okay, so they are dated to be around. I don't know why this thing came here. This line here, this strange.
Yeah, somebody is, please, do not write on the screen or anything. Thank you so much. I think somebody did it. Let me see if I can erase it, Bhaskarji, but I'm
Hmm.
just going to check. Yeah. Thank
Hmm.
you.
Okay,
Yeah.
okay. So I'll just carry on in that, till then, right? Mm. Yeah. So they are dated to be about 800 BCE, but they are like, this date comes from like during the time of the British Indologists, the Western Indologists, British and German Indologists, and that time it was the trend to really post date the Vedas. So in fact, they could be much older than this stated date of 800 BCE, and they also make it clear that they are repeating rules which were known for many centuries before then. So okay. So the two things that I'll be focusing on in this talk is the so-called Pythagoras theorem, its applications in the Vedas, and a result for the square root of 2, an approximation for the square root of 2. So this is the famous result given in the Bodhayana and the Apastamba Sutras. So here is the original Sanskrit, and the English translation goes as follows: that if you have a rectangle of sides A and B, and the diagonal is C, then the area of the square of C is equal to the area of the sum of the squares of A and B. So A square plus B square equal to C square. So and this and just as a orientation, Pythagoras was lived sometime in 500 BCE, and Sulbasutras, even by these conservative estimates, are at least 300 years before Pythagoras. So there is one more sutra, very interesting sutra in the Sulba Sutras, which if you have two squares of given sides, which I have called here A and B, you want to create a new square alter whose area is equal to sum of the squares of A and B. So in other words, A square plus B square should be the area of the new square. So how do you make this construction? So it goes as follows: you make a line here B, which is equal to the side of this square, and you create this diagonal. So this diagonal, and make the square of that. So this square will be equal to has the area equal to A square plus B square. And this you can see immediately by an application of the so-called Pythagoras theorem, because in this right angle triangle, C square is equal to A square plus B square. So the very interesting point about this construction is that from this construction you can also do the reverse. That is, starting from this construction, you can see why the Pythagoras theorem is true. So-called Pythagoras theorem is true. So because if you start off like this, I have shown here again these two squares, and I have this shown here, this rectangle with sides A and B, and we have this new square of side C. And if you consider these two right angle triangles, this one and this one, which here I've shown in the color red. So right now the area of this blue region is A square plus B square, and it's still A square plus B square, this red plus blue areas. And now we just move these triangles here, this one here and this one here, and so we get a new figure, this square we get, and the area has not changed. The area is still A square plus B square, but that is, now you can see this area is equal to C square, the area of this square. So you have the fact that A square plus B square equal to C square. So the Sulba Sutra constructions, they even contain implicit reasonings or proofs of the so-called Pythagoras theorem. And this was noted by various scholars. So, for example, Vibhuti Bhushan Datta, he mentioned this in the Science of the Sulba in the 1930s. A little bit earlier, this was observed by a German historian, Konrad Müller, in 1929. From his article, I have given his this text here, and a more comprehensive history can also be found in Amartya Kumar Datta's article in 2022 in the Bhavna Mathematics Journal. So this is the very interesting part. Now, when we come to the connection with Pythagoras, what is the, because people usually believe that this result was discovered by Pythagoras and it was proven by him. But when you actually look into the history, there is actually no evidence that this result was either known to him or it was proved by him. So this is stated categorically by Thomas Heath in his 1921 book. So Heath is one of the biggest admirers of the Greek mathematicians. So when it comes from a person like Heath, you can be pretty sure that it's going to be like a little bit of a conservative statement. But even he says that there is no evidence that this result was discovered by him. And yeah, so basically this is from his book, A History of Greek Mathematics, Volume 1. So he has explicitly stated, I don't have the snapshot of it right now in this presentation, that there is no evidence that this was discovered by him. So, I mean, this was also discussed by other by historians of mathematics like Hermann Hankel, and in his book, I don't remember the title, but it was in German, and he repeats, Hankel's claim, and Hankel even, claimed that he did not even discover this result. So Heath tries to cover that up, the statement by Hankel, and then he also, as you can see, he alludes to India, the Sulbasutras, and then he sort of tries to downplay the importance of the Sulbasutras, even though the Sulbasutras were, as we saw, 300 years, at least 3 centuries prior to Pythagoras. Then yeah, there are here some more statements here, which I probably will not be addressing here, from Hermann Hankel and from Thomas Heath, works from them, where this thing is again like repeated. Uh, so it's very interesting that even though Pythagoras, there was no evidence to link Pythagoras to this result, either by way of discovery or proof. It is still very interesting, how this narrative has established itself in the modern world. So to understand this in a little bit more detail, it would be nice to have a look at how the Sulbasutras were introduced to the West, and how the reception in the West was to the Sulbasutras. So the first introduction of the Sulbasutras was by the writings of George Thibaut. He was an Indologist, originally from, I think, Austria or Germany, but in the from the German Austria region. But he was yeah, he was connected with the British Empire, and he he wrote in the Journal of the Asiatic Society of Bengal in 1875, where he translated parts of the Sulbasutras, Baudhayana Sulbasutra mostly, and there he, it was not the entire Sulba Sutras in its entirety, but parts of it. But even this was enough to show to the Western world that the origin of mathematics could very well be the Sulba Sutras and not Greek geometry, because Greek geometry was considered to be the starting point of all of mathematics till that time. So yeah. So actually this made it clear that the Indians had a geometry of their own that was, number one, independent of the Greeks, and number two, it could since if he did not state any dates, Thibaut, but if it was coming before the Greeks, then it was a possibility that the Greeks were not the inventors of the mathematical tradition, or plane geometry at least. Right. So this is the sudden consequence that the Western historians had to deal with, and this was obviously very tricky, because the whole notion of colonialism in those days was based on the belief that yeah, a better people rules over the lesser people. So this would not be justified anymore. So this was in fact also pointed out by Abraham Seidenberg in his 1978 article, The Origin of Mathematics. So he says Thibaut did not formulate the obvious conclusion that the Greeks were not the inventors of plane geometry, it was the Indians. This was the message the Greek scholars saw in this paper, and they did not like it. If the Indians invented plane geometry, what was to become of Greek genius or the Greek miracle? So to counter this, there was a lot of activity amongst the European mathematicians of that time, historians of that time, and the movement was spearheaded by Moritz Cantor. He was the most influential of the historians of mathematics in the second half of the 20th century, starting from the 1877, 1880s onwards, and he started this reaction to the discovery of the Sulba Sutras in his 1877 article, where he assigns a date of 140 CE or 140 AD, as you wish, to the Sulba Sutras. So yeah. So, and this a much more recent date, comes much later than the Greek dates assigned to the Greek mathematicians. And from this, he concludes that the Sulba Sutras, they had their origin in Greek geometry. So it was the Greek geometry which served as the the origin of the Sulba Sutras, and they were derived from them. So he also assigned a date of 140 CE to the to Panini. So based on some very questionable Sanskrit yeah scholarship basically. So yeah, I won't go into this detail because it will take some time. But here are the the snapshots from his article. So, and this is something which he, and in 1880, he wrote his very well-known book called Lectures on the History of Mathematics, here, Vorlesungen über die Geschichte der Mathematik. So, in this book, he again assigns a date of 140 CE to the Sulbasutras and claims that it has Greek origins. And he also, like, and as regards to the Pythagoras theorem, it's interesting to see what he has to say. In this book, he claims that Pythagoras, he got his so-called theorem from himself, and he may have had got it a little bit, the idea of from Egypt, but in essence it was his. So this was the claim that he sort of made. So for example, this the snapshot from his book in the original German and translation. Some of the things which belong particularly to the history of mathematics we will not refrain from attributing to Pythagoras himself. Amongst them is the Pythagorean theorem. So as of now you can see the Pythagoras theorem belongs to Pythagoras. This was the state in 1880. Okay. So yeah, so this is I just stripped. So and then in as time went on in 1884, this was basically the general picture that Cantor's views held a lot of influence in the mathematical and historical circles, and it was taken to be taken for granted that the Silbasutras came from Greek geometry. But there were a few Indologists. One of them was Leopold von Schroeder. He wrote an article in German called Pythagoras and the Indians in 1884, where he discusses in detail the philosophy of Pythagoras, the mathematics attributed to him, and he compares it in detail with the philosophy of the Hindu and Buddhist traditions and the mathematics of the Sulbasutras. And there, for example, Pythagoras also was a believer in the theory of transmigration of souls, the cycle of birth and death, and the theory of karma, and all these kind of typically Hindu beliefs. And he makes a very detailed comparison of these two traditions, and he claims with the utmost confidence that Pythagoras must have also got his mathematical results from India, and which also makes sense because in the sense that if the philosophy of Pythagoras is so similar to the Hindu philosophy, and if the Hindu philosophical texts, that is the Vedas, they contain the Sulbasutras, which in turn contains the so-called Pythagoras theorem, for which Pythagoras in turn is famous, then obviously it becomes a very strong possibility that he could have got this result from the Hindu sources. So this is and he dismissed Cantor's date of 140 CE for the Sulbasutras, and obviously he put a date which was older than Pythagoras for this. So here are some more snapshots from his article where I basically the things that I said just now are kind of stated explicitly. So yeah, I would probably, yeah, maybe I just read out this one. We are inexorably forced to the conclusion that Pythagoras took the teachings of the five elements, etc., just like his theory of the transmigration of soul, his mathematical theorems from the Indians, and brought it to Greece. So this also includes the so-called Pythagoras theorem. So in 1894, Cantor, he came up with his next edition of Lectures on the History of Mathematics. So in this 1894 edition, he persists with the claim of the Greek origins of the Sulbasutras and 140 CE as their date. So this is really interesting because, in fact, we know today for sure that Leopold von Schroeder had sent a copy of his article to Moritz Cantor, because Cantor he stated this in one of his later articles. So he knows about this article by Schroeder, but he persists with this claim. So he dismisses them on the basis of faulty dating. And we come back in 1899. From 1894 we come to 1899 to an article by George Thibaut. So remember, Thibaut was the guy who originally introduced the Sulbasutras to the West. So and Thibaut was very much waxing praise about the Sulbasutras in his original article in 1875. But now he sort of changes his language a little bit, and he sort of gives into Cantor, saying that, but he still claims that the date of assigned by Cantor is wrong, and he still claims that the Sulbasutras are older than Pythagoras and the Greek geometry. But he says that it is something not very special, the Indian geometry, and and in general one finds nothing in the geometry which was not known to the Greeks. So he repeats some of the cliches of Cantor, which I probably will not discuss right now, but he tries to counter Cantor's views on the Greek origins of the Sulbasutras very hesitantly. I mean, it's very like he's very hesitant and very apologetic in his language. He's written this in German. I've given an English translation here, but he's very apologetic in his language. You can make out. Yeah. So now, this was in 1899, and the next step in the historiography of the Sulbasutras is in 1901, when another German Indologist, Albert Burke, he gave a translation of the Apastamba Sulbasutra into German. And there again, from his dating, he was stating explicitly that the Sulbasutras came before Pythagoras. And somehow or the other, it is not clear why, Moritz Cantor, he had a change of heart after reading the article by Albert Burke, and this is what he says in his 1905 article on the oldest Indian mathematics. So this is in the original German. So and there he's like, earlier he used to say that Pythagoras proved the Pythagoras theorem by himself with hardly any input from the from Egypt or anywhere else. But now when it becomes clear after the article by Albert Burke that the Sulbasutras they predated Pythagoras, instead of admitting of the possibility that Pythagoras could have got his mathematics from India or from the Sulbasutras from Indian sources, he suddenly turns to Egypt as the possible source for the so-called Pythagoras theorem. I mean, even here it's like he's very much measly, let us say, in his concessions. So because his idea is that the Egyptians knew the triangle 3 4 5 with sides 3 and 4 and 5, and from this he claims that Pythagoras observed that 3 square plus 4 square is equal to 5 square, and from this he derived the general result and proved the general result. This is the claim that Cantor makes in his article. And in this article, in 1905, he suddenly discovers the wonders of Egypt. Like so it is, yeah. So from where Pythagoras could have obtained his result from the 3 4 5 triangle at least. Right. So in this article, as I said, he claims he got it from Egypt, so the 3 4 5 triangle. But earlier he made no mention of where he got this 3 4 5 triangle from. Um, okay. So here are certain other yeah, snapshots from his article, which I won't go into right now. So as an interesting comparison, we can also jump a little bit ahead in time in 1921 to Thomas Heath. So so his treatment of the Sulbasutras is very dismissive. So he says that the Apastamba Sulbasutra, he dates it to 5th or 4th century BCE. There is a proposition stating the so-called Pythagoras theorem in general terms, but without proof. So he has a problem that it is without proof, and then there is in general a downplaying of the Sulbasutras in his article. There is no sign of any general proof. It is founded on just an imperfect induction from a certain number of cases, etc., etc., etc. But he is pretty sure that this result, so-called Pythagoras theorem, was discovered by Pythagoras, and he even tries to fabricate certain proofs of how Pythagoras could have proved this result. So this is just as a comparison. So this was the situation till the early 1920s. Now, when we go a little bit further in time, 1924, 25, 26, the the study of Babylonian mathematics started gaining a lot of attention in this time. This was led by the historian of mathematics by the name of Otto Neugebauer. He was an Austrian physicist, historian of mathematics, and his works were very influential in making Babylonian mathematics very well known all over the world. So, just as an orientation, the Babylonian civilization is dated to about 1700 BCE, and in fact, as I have stated here in this text, that the Babylonian civilization is connected to the area known as the Mesopotamian region, and Mesopotamia is actually the land between Euphrates and Tigris in the region in Iraq. And the word literally means between rivers. Meso would mean between, and Potamia means rivers, so between rivers. So this region is called Mesopotamia, which is the Greek name for this, which was revived with the discovery of this region. And yeah, the mathematical texts are dated to um, yeah, 2500 and 300 BCE, and so basically they come from this they come from this region. So yeah, so as I said, from the like mid 1920s on, or so onwards, Neugebauer's work started becoming more and more, they started getting more and more attention. And so in this, he sort of, the focus shifted of the when it became clear that Pythagoras could not be considered as the originator of the so-called Pythagoras theorem. The focus shifted to Babylonia as the source for the so-called Pythagoras theorem. So it's very interesting that there was a pretty long amount of time, let's say from the time of, at least from the time of Leopold Schroeder's article in 1884 till the 1920s, when Babylonian mathematics was not known, and when the Sulbasutras were clearly, they predated the times of Greek geometry and Greek mathematics and Pythagoras. So one would have expected that, the Sulbasutras to have been considered as the source of the so-called Pythagoras theorem and Greek mathematics, but now it was not the case. But now, with the discovery of Babylonian mathematics, the focus suddenly shifts of the so-called Pythagoras theorem and even the entire Greek mathematical tradition as having its origins in the Babylonian mathematics of the region of Mesopotamia. So yeah, so this is like, one can see this difference in treatment between the two civilizations. So in 1928, Neugebauer, he wrote one of his earliest articles on the history of the Pythagorean theorem in German. So he, like, he considers us basically a cuneiform tablet of Babylonia, where an approximation is given for the diagonal of a rectangle with sides 10 and 40. And obviously it's not stated that this approximation is not stated the way I've given it here in this text here. A square root of 1 plus x is approximately equal to 1 plus x by 2. There should be an approximately equal to sign here. But he assumes that they knew this approximation, and and that they knew, and that he, in this article, he further claims that this is as evidence that the Babylonians knew the so-called Pythagoras theorem, and suggests the Babylonian mathematics as the common origin of the Sulbasutras, and the mathematics attributed to Pythagoras. So here is this original German text. The Yeah, the difficulties which direct borrowing of India, the difficulties which direct borrowing from India gives rise to, they fall away under the assumption of Babylonia as a common source of the mathematics of the Sulbasutras and Greek geometry. So, right. So the difficulties which arise from assuming a direct borrowing from the Greeks from India fall away on the assumption of a common origin in Babylonia. So, and then in 1935 and 37, he wrote a very influential text called Mathematical Cuneiform Scripts texts, which was translated into English in 1945. And there there is, he discusses this the so-called YBC 7289, which is a clay tablet from Babylonia, which discusses the square root of 2. So this is this clay tablet from Babylonia. You can see there's a square of square is shown here, and we are required to find out the diagonal of the length of the diagonal of this square. So if you like, there is then certain numbers are given in the Babylonian script, which translates to 1, 24, 51, and 10. So this would be in the sexagesimal system used by the Babylonians. So when you like, when you convert that to our well-known decimal system, it would be like 1 plus 24 by 60 plus 51 by 60 squared plus 10 by 60 cube. And this is indicated as the length of the diagonal, and there is no doubt that this is an extremely accurate value for the diagonal of a square of length 1. In other words, the square root of 2. And this is accurate to, like, 6 decimal places. And so I mean, but obviously you have to remember that it is for a square of, and from a square it is fairly easy to see that the sum of the squares of the two sides equals the square of the hypotenuse, because it's like, you just have to, like, it's from symmetry considerations, it's pretty easy to see that, as opposed to the general rectangle where the sides are unequal. So yeah, so, and interestingly, there is also a value for the square root of 2 in the Sulbasutras, in the Baudhayana Sulbasutra, and there the value is given in this form: square root of 2 approximately equal to 1 plus 1/3 plus 1 by 3 times 4 minus 1 by 3 times 4 times 34. And this is accurate to about 5 decimal places, a little bit less accurate than the Babylonian value. But the accuracy of the value is not the um, point under discussion right now. The point under discussion right now is the claims that Neugebauer makes as to how the Babylonians arrived at this value of 1, 24, 51, and 10. So he assumes or he claims that the Babylonians got it from pretty sophisticated algorithm for finding out the square root of a number, which is actually uh, in practice very simple to understand, but by its conception, it's a pretty sophisticated piece of thinking. It's a well-known algorithm for finding out the square roots. So if you want a square root of, let's say, the number n, if you start off with some guess, let's say ri, and the next guess you replace ri by half of ri plus n by ri, so it will be somewhere in between ri and n by ri. So you will see that if you keep on making this iteration again and again, these two numbers will keep getting closer and closer, and you will have finally r equal to n by r. So r square is equal to n, so which means that r is the square root of n. So this is a well-known algorithm, for finding out the square root. And he claims that this is the algorithm they used for finding out the square root of 2. If you start off with 3 by 2 as the initial guess for the square root of 2, about 1.5. So this is obviously a very strong claim, and it would be like, yeah, okay, I am a little bit. Now the thing is, yeah. Um, Maybe I will come to this in a few slides. I just wanted to perhaps talk more about this Sulbasutra value of square root of 2. So the square root of 2 in the Sulbasutras is given by this relation, as I said, and there were many attempts to find out how the Sulbasutra authors arrived at this result. One of the most commonly accepted one is the one given by Vibhuti Bhushan Datta. I will not go into the details of this. It's a little bit like too much for this talk. And but he gives a basically geometric method where you kind of rearrange a square of side 2 and 1. So the area of this rectangle of sides 2 and 1 is 2, and you try to rearrange this rectangle into a square. That is the basic idea, and this is also one of the sutras given in the Sulbasutras. Okay, so when you arrange this rectangle into a square, the square will have the same area, that is 2. Therefore, its side will be square root of 2. Okay, so how do you make the rearrangement? So that's the question, and obviously you will not get a perfect rearrangement because square root of 2 is not a rational number. So you sort of you kind of he gave a method of how they had done this. I have discussed this in detail in my article, the third article, which I'm not discussing today. And this idea by Vibhuti Bhushan Datta was actually then extended by the American mathematician David Henderson in his article Square Roots in the Sulbasutras. So there he extends this method, and you get an infinite series expansion, infinite series for square root of 2. So this is this Sulbasutra approximation. Then if you follow the method of Vibhuti Bhushan Datta as Henderson had done, you get the next term as this, the next term as this, and so on and so forth it goes. So you get a sequence 3, 4, 34, 1, 1, 5, 4, 1, 3, 3, 1, 7, 1, 4, etc. So this is a very interesting application insight from the Sulbasutras. Now it's very interesting to see that you get exactly the same result also from the iterative algorithm which I just spoke about, and which Neugebauer imposed on the Greeks, who claimed that the Greeks got used this algorithm. So but but the thing is that you can uh, make such a claim only when you see that the fractions that you get, like starting from the initial fraction of, let's say, 3 by 2, and then you applying this iteration again and again. When you make the compare the fractions, then you can say that, okay, this could have been used. If you use just a decimal or a sexagesimal representation, that will not give you much information, because it's this result, this representation is independent of how you arrive at it, including the iterative algorithm proposed by Neugebauer. But the interesting thing is that if you start with 3 by 2 and you go to the first iteration of the square root algorithm, this one, right? The next number you get is 17 by 12, which is nothing but the first 3 terms of the Sulbasutra expansion. Then if you go to the next iteration, you get the entire Sulbasutra expansion, which is this. And if you go to the next term, you get the this term which I had just shown here earlier in the slide, which was obtained by Henderson, and so on and so forth. And interestingly enough, this geometric method is entirely equivalent to the square root method. And why it is so, you have to do a little bit of calculations, and which I have shown on my article. But in the like, here in this expansion, you nowhere encounter the fraction 30547 by 21660, which in fact is the fractional representation of the Babylonian number 1245110, which we saw just now. So it's a leap of imagination to claim that they used this algorithm to obtain this. And if you make a comparison to what Heath said about the same result of the Sulbasutras in 1921, so he says that the length of taken is an approximation to square root of 2, but the author does not say anything which suggests any knowledge on his part that the approximation is not exact. That means he's saying that the Sulbasutra people were not aware that this is just an approximation. So which is of course false, because the sutra includes the word savisheshaha, which means that it is an approximation. So they knew that. And yeah, so I just, maybe I'm running a little bit short of time. Maybe I'll just try to make it a bit faster. We come then to the next artifact of Babylonian mathematics, which played such a huge role in this narrative of Babylonian mathematics. That is so-called Plimpton 322. So there you have a column of different numbers, and this was deciphered by Neugebauer to satisfy the relation a square plus b square equal to c square. And with this, it sort of, it was taken as conclusive proof that the Babylonians knew the so-called Pythagoras theorem. And actually, to be fair, it's also there's also a good amount of evidence that the Babylonians knew the so-called Pythagoras theorem sometime in 2000 BCE, 1700 BCE, or so on. Okay, and yeah, but my point here was to show the number one, the sort of, the difference in the reception of the Sulbasutras and Babylonian mathematics. So why is there this difference in accorded to the mathematics of Babylonia and the mathematics of Sulbasutras? Remember, when the Sulbasutras came out, they were immediately dismissed as something, that post-dating Greek geometry, as being derived from Greek geometry. And or if you look at the works of Heath, they were somehow not so important. They were, very immature pieces of mathematics. Whereas when you look at Babylonian mathematics, you will see suddenly historians suddenly, attributing the most sophisticated algorithms to Babylonian mathematics, and so on. So why is this difference according to Babylonia and the Hindu civilization? So this, unfortunately, I will not be able to address in this talk, but I have discussed this at length also in the first article that I had shared in this talk on my Substack blog. So it has more to do with, the Babylonia as being a biblical city. So it has its, very biblical connections, and it was yeah, a lot of connections with the Bible. So it sort of, it puts it on a sort of, Western uh, trajectory of history, so to speak, and that is one of the reasons. So which has also been pointed out by other scholars, but I will not be going into this right now. So what I would like to conclude with is a discussion on the importance of the Sulbasutras. So before I go to the importance of the Sulbasutras, the consequences obviously is that, because of the work starting from Moritz Cantor, then Thomas Heath, and Otto Neugebauer, the Sulbasutras have been literally removed from any serious discussion on the history of mathematics. And all the history of mathematics, goes to Babylonian mathematics as the precursor of Greek mathematics. Okay, so and Mesopotamia is depicted as the origin of mathematics, as the origin of civilization. So this, maybe I just also mention here very slowly that, because in the way history is conceived by, like, let's say, like by Hegel, the German philosopher, or by the general Western worldview of which was created during the colonial times, civilization goes in a linear fashion from less developed to more developed. And so Mesopotamia fits that picture as the cradle of civilization, which passed on to the Greeks and which passed on to Europe and to the Western world. So basically, this is the very rough idea for this. So these are some of the consequences of this kind of research on the history of mathematics. So and now I would like to conclude with the importance of the Sulbasutras, having discussed about the historiography. So the Babylonian precedence hinges critically on the dates assigned to the Sulbasutras. So the Sulbasutras have been assigned a date of 800 BCE. So as we said, like I don't know how reliable these dates are, and there was a strong tendency to date the Vedas to a much more recent time than they actually were. So we don't know, if this how reliable this date of 800 BCE is. Maybe I'm sure there will be some scholars in this conference who will be more informed about this than I am. Then there is also the fact that Greek philosophy is similar to Hindu philosophy, number one, and number two, the Greek religion, the so-called, they had their own gods, they had their own altars for these gods, just like the Hindus had Vedic altars, and like, as I have also discussed in my book, there is this, you cannot it becomes a pretty strong possibility that even the Greeks got parts of their mathematics from the Indian Sulbasutras, as I have discussed in my book. But this thing, this importance of the Sulbasutras was addressed very in a series of two articles by Abraham Seidenberg in 1962 and 1978, called "The Ritual Origin of Geometry and the Origin of Mathematics." So here he says that, okay, even though the Babylonian mathematics is supposed to be 1700 BCE, and this was a tendency also by Neugebauer to claim Babylonia as the origin of mathematics. He makes a very deep analysis of Babylonian mathematics, of the Sulbasutras, and of Greek mathematics, and he comes to the conclusion that from the mathematical content, Babylonian mathematics cannot be the origin of Greek mathematics or the Sulbasutras. Rather, it is a mathematics which is very similar to the Sulbasutras, which is the origin of both Babylonian and Greek mathematics. So, and he says in his article that the Sulbasutras have never taken the position in the history of mathematics that they deserve. And here he says, after a long and detailed comparison of the mathematics, he says that a common source for the Pythagorean and Vedic mathematics is to be sought either in the Vedic mathematics or in an older mathematics very much like it. The view that Vedic mathematics, that is Sulbasutra mathematics, he talks about, the view that Sulbasutra mathematics is a derivative of old Babylonia has been rejected on the basis of the study he did. So then he postulates, what was this older common source like? He says that, I think its mathematics was very much like what we see in the Sulbasutras, which obviously follows from the statement that a common source is to be found either in the Vedic mathematics or in an older mathematics very much like it. So he says that it was very much like in this what we see in the Sulbasutras. So, but the question now arises, if they are very much like the Sulbasutras, why not the Sulbasutras themselves? Well, there are 2 points. One was that the date assigned to the Sulbasutras in 800 BCE was one of the things which made him not say that it's the Sulbasutras themselves. And the second one was his theory of it's not being the Sulbasutra itself hinges critically on the so-called Aryan invasion theory, which we know was initially fabricated by the European colonizers to justify colonization. So both of them are actually suspect in today's from what we know today. And so the yeah, so basically this sort of makes it very important to revisit the role played by the Sulbasutras in the history of mathematics. So I've come to the talk of my end of my talk, and I have forgotten to put a